Welcome everyone. It's my pleasure to introduce our speaker today, Dr. Sean Pike from here, UC San Diego. Sean did his undergraduate at Brown University, and then he did his graduate work at Caltech, working with Dr. Fiona Harrison on UStar, and he's going to tell us about that work today. So Dr. Harrison is also my postdoc advisor, so we have some genealogy there in common. So Sean has joined us to work on the COSY satellite, which I don't think he's talking about at all today, but that's what he's currently working on here as a postdoc at UC San Diego. And in addition to Sean's excellent scientific work, he also has been a very strong advocate for equity, diversity, and inclusion, and he is currently organizing the working group on EDI for the COSY mission. So we're really happy to have Sean on board for multiple reasons. So welcome, Dr. Sean Pike.
Great, thanks, Steve. Thanks everyone for coming. As Steve said, I'm going to be talking about my X-ray astronomy work with NuSTAR primarily. And so a lot of this is going to be from my dissertation at Caltech, but I've got some new stuff I want to share as well. So the idea today, I think, is to really give folks an idea of what we can learn in X-ray astronomy generally, and in particular, what we can learn using NuSTAR, because that's where my expertise lies. And so I'm going to give a little bit of a sampler of a couple of different X-ray binaries that I've worked on, and a little bit of background on that as well. So I'm going to start by giving an overview of what an X-ray binary is. I think probably this is familiar for a lot of folks, but I don't know what everyone's background is, and I assume we've got students here as well. So an X-ray binary very generally is formed when a compact object like a neutron star or a black hole accretes material from a companion star. And that companion star may be a mean sequence star or an evolved star. But accretion can happen in a couple of different ways. I'm showing a couple cartoons here to demonstrate that. The first is via accretion of winds. So the companion star is blowing off heavy winds. Those winds fall into orbit around the compact object, accrete onto the object, glow in the X-ray. But the other way that accretion can happen, the other sort of channel, is through Roche lobe overflow. So in this case, the companion and the compact object are close enough to one another that the companion fills its Roche lobe. Material actually falls directly off the surface through the Lagrange points and into orbit around the compact object. So I'm going to focus on that because those are the kinds of objects that I'm looking at most of the time. Okay. So when the companion star shown in green here fills its Roche lobe, this material falls into orbit around the compact object, forms a circular-ish orbit around the neutron star or black hole. And generally, you might think, okay, well, it just stops there and we just have this weird ring. But what we see is there's evidence that essentially angular momentum is transported in this ring, right? Internal friction within the accreting material transfers angular momentum outwards, which means that the material starts to spiral inwards towards the compact object and forms what we call an accretion disk. And so as that happens, the gravitational potential of the material that was accreted is transformed into thermal energy. And by the time that we get to the inner regions of this disk, very close to the compact object, sometimes all the way up to the surface of a neutron star or to the inner...
You could, if you click more, you can get rid of that thing, like hide the panel.
I'm not sure where my mouse is, though.
Are you doing a second?
I am, but...
Oh, yeah. Sorry, I learned this.
I can't. Do you see my mouse? I can't see my mouse.
Yeah. Oh, maybe because you're...
Because I'm in full screen mode. I think it'll be okay. I think I'm saying the things that are behind there, so it'll be fine. So as material falls inwards, it gets really hot, right? And so as we reach the inner regions of the disk near the surface or near the compact object, it can reach temperatures of tens of millions of Kelvin, and which corresponds to about 1 to 2 keV. And so it emits a ton of X-rays, and so that's what we're really looking at. And so when we look at the spectra of these things, right, we're seeing that thermal emission, which indicates the presence of a disk. And this is represented by a multicolored black body. So essentially you have annuli of changing temperature, right? So really hot, close to the compact object, cooler as you go out. And then we also see evidence for non-thermal emission, which generally has like a featureless power law shape. And we attribute this to a region of hot plasma known as the corona, which here I'm showing is sort of like a jet base or something, or a lamppost. But it's not really clear exactly what the shape of that corona is in all cases or where it is in the system. But we know it's close to the disk and it's close to the compact object. And an important sort of point that I want to bring up here, because it's going to come up later in some of my work, is that luminosity, the brightness of these things, scales directly with the accretion rate. So the amount of material falling onto the compact object is directly proportional to the luminosity of the system. And so we can represent that proportionality using this eta parameter, which is sort of an efficiency. And that's related to different properties of the system, but it's usually around 10%. So this is one of the most efficient methods of transforming or of creating energy essentially in the universe. And so what I've discussed up till now is applicable to both black holes and neutron stars. An important difference between these two systems is that in a neutron star, you can have very strong dipolar magnetic fields. And depending on the strength of those magnetic fields, if they're strong enough, essentially the magnetic pressure can counteract the ram pressure of the material in the disk and lift it out of the disk, right? So the disk gets truncated, it's cut short, and material is funneled onto the poles of the neutron star. And so I'm showing those poles in green, and so as material is funneled onto it, it creates hotspots. As those hotspots move in and out of our line of sight, they create X-ray pulsars. And at high accretion rates, that material becomes shocked as it's falling onto the poles. And rather than just having a hotspot on the surface, we get what we call an accretion column, where material is essentially piling up faster than it can spread over the surface. And so that just produces different kinds of timing signatures and spectral signatures. And so zooming back out, this is kind of our picture of what an X-ray binary looks like. We've got our companion star on the right, and there's a neutron star or black hole or something on the left in the middle of that disk. Material is spiraling inwards. Sometimes we get outflows in the form of jets that are shown here. And every sort of section of this picture is irradiating in a different bandpass. But X-rays give us a direct view of the regions right near the compact object. So it lets us study those black holes and neutron stars very closely. In many of these systems, you know, that kind of disk picture is persistent. So, you know, it's always glowing with this like disk black body plus power law kind of spectrum. But most X-ray binaries are transient, meaning that for a long period of time, they're in a quiescent state, very low luminosity. And then every so often they go into outbursts, and these outbursts can last on the order of days to weeks or months, depending on the object and the size of the disk and things like that. And these outbursts themselves have different causes. So in some cases, it's what we call the disk instability model, where the accreting material surpasses a certain critical ionization, for example, and then all of a sudden that friction jumps up, that internal friction jumps up, and the disk drains, and we see an outburst then. But in some cases, which I'm showing on the right, we have neutron stars in orbit around in highly elliptical orbits, where we see these outbursts, these periods of outbursts, which are shown as these black. Do I have a pointer?
In the ruler just behind me.
So yeah, this is showing for a number of different objects. These are different X-ray binaries with neutron stars and high mass companions. They're sort of duty cycles. So these black bars are outbursts that they're going into. And so this occurs when, in these specific systems, this happens when the neutron star passes really close to the companion star and picks up a bunch of material, and then it has a disk for for a little bit that irradiate for a long time. And on the left, I'm showing sort of the evolution of X-ray binaries throughout their outbursts. And they tend to trace out this sort of Q diagram here. And so in general, in quiescence, they're somewhere down here, right? So that y-axis here is their intensity, x-axis is their spectral shape, essentially. And so they spend most of their time down here, low, in the sort of low intensity state. And their spectra are hard, right? Because we're mainly looking at that hot plasma, and there's no, the disk is not coming really close to the contact object, and so we don't have that thermal emission. But when they go into outburst, when that disk does form and starts draining and starts going towards the contact object, we get an increase in intensity, and they kind of round this track here, where we see more and more thermal emission and less of that parallel emission as it goes on. And we have different sort of regions are filled by different kinds of X-ray binaries. So black holes kind of take this path, and then neutron stars have a slightly different kind of behavior.
That because of the hot spots that you get.
Yeah.
higher.
Yeah. So this is, you're seeing just like higher accretion rate onto the hotspots, essentially.
So.
Mhm.
Yeah, so. The top of the luminosity there is roughly kind of an Eddington luminosity limit, is that right?
Yeah. So
I'm guessing that's kind of a solar mass. I mean, 10 to 38 ergs per second, but that's of course in just the X-ray band.
Yeah.
You're looking at.
Yeah. So for a solar mass accretor, or comparable, the Eddington limit's around 10 to the 38 ergs per second. So this is when the radiation pressure is counteracting the pull of gravity, essentially like halting accretion. But we know that objects do surpass the Eddington limit by even like our regular X-ray binaries can surpass their Eddington limit by factors of a few due to like beaming and things like that. But we also have these ULXs, which are extreme versions of X-ray binaries, which can surpass their Eddington limit by factors of tens, hundreds, and or more. So, but I'm not going to be talking about ULXs too. Okay, so why do we study X-ray binaries? I think one of the sort of my go-to answer for this is, aside from that they're cool and fun, is that they're a good, they're the best laboratory we have to study accretion in general. And accretion is an important process across a lot of different timescales and a lot of different mass scales. In particular, accretion onto AGN has ramifications for galactic feedback, for evolution of supermassive black holes, etc. But the variability of accretion in AGN are timescales that are not reasonable for people to study. It's like hundreds of years or something like that. And so, but in X-ray binaries, these outbursts last for a year max. So that's an amenable timescale for grad students and other human beings to study. And in general, they also represent important laboratories for a lot of different interesting subjects in astrophysics, because we're looking really right at the regions near the neutron star or black hole. We can study regimes of strong gravity, strong magnetic fields, evolution of binary systems, because we're kind of at a point where one of the stars has already undergone its life cycle, and then exotic states of matter in the form of neutron stars, where we can get constraints on mass and radius to help us understand the equation state of neutron stars. We study X-ray binaries with a number of different X-ray telescopes. Most of these lie in what we call the soft X-ray band. And so here there's just a list of a bunch of X-ray telescopes that I pulled from the HESARC and the energy range that they cover. And so a lot of these cover this soft energy range, which is like 0.1-ish to 10 keV. And that's really capturing that thermal emission that I talked about, so studying the disk in detail, and it can help us constrain things like absorption and the presence of iron emission. And iron emission is, as I'm going to show a little bit later, is a really important tracer for these systems. And then beyond that range, we have the hard X-rays, which capture that non-thermal emission, so the corona that I was talking about. And so I'm going to specifically be talking about work done with NuSTAR, which is a hard X-ray telescope that has that extends its range somewhat into the soft band as well. And it does this by combining these, let's see, there we go. Combining low incidence angle scattering optics with semiconductor detectors here, and a focal length of about 10 meters, right? So NuSTAR went up in about in June 2012, and while it was in space, it extended, it stretched out to its 10-meter focal length. And the combination of these custom optics and custom detectors means that it can look at the X-ray sky in the 3 to 79 keV band with good angular resolution, good spectral resolution, and fantastic timing resolution, which makes it really useful for doing a lot of complex analyses of timing and spectral properties. So now I'm going to talk about a couple of sources that I've studied using NuSTAR and what we can learn from them. So the first I'm going to talk about is MAXI J 1848-015. This is a black hole X-ray transient. So in when was this? This was like Christmas-ish 2020. I was just about to go on vacation, and this thing went off in the sky. It was detected by MAXI, which is the Monitor of All Sky X-ray Imager. This is an all-sky X-ray telescope on the International Space Station, and it detected a new X-ray transient right around here in the sky. So this is just this is an all-sky map of different X-ray transients that have been observed by MAXI. This orange here is the sun traveling across the sky over the year, throughout the year. And then this orange blob that I'm showing here is the region in which most X-ray telescopes cannot look at things, right? Because they'll be blinded by the sun, essentially, right? And so when this thing went off, it was close enough to the sun that other observatories couldn't look at it, but NuSTAR is special in that it is able to look at the sun and near the sun. And so we asked for some time to look at this source because NuSTAR was the only one that could do it. And we got two different observations of this source during outburst, right? So this is an X-ray transient, went into outburst somewhere around here, and then the peak of its outburst lasted around 7 days. And we got our first NuSTAR observation right near the end of that peak, so just in time before it starts simmering down a little bit. And then later on, we got a second observation. That's the combination of coverage across this transient's outburst was really key to the analysis that we ended up doing. And so one of the goals of these observations was to determine what is it? Is it a neutron star? Is it a black hole? And then to characterize the source as well and to localize it. So MAXI can't localize sources very well. It needs this kind of follow-up from other missions in order to tell where a thing is and determine, is it associated with something we know about already, or is it not, or is it something brand new? And so thanks to this first NuSTAR observation, we were able to localize the source to a region of 90 arc seconds, which is still not great, but better than MAXI. And then that laid the groundwork for future observations. And so we got a much better localization with some other observatories. And so by March, a few months later, essentially, we knew it was definitely not consistent with anything previously cataloged. So this is a new source, and we knew that it was coincident with this galactic cluster glimpse C01. And another thing we found is that it has the soft state luminosity, or when it was at the peak of its burst, it had a very low luminosity. So I mentioned earlier that the Eddington luminosity for an accretor with around the mass of the sun is about 10 to the 38 ergs per second, right? So something like a neutron star, that would be its Eddington limit is 1 to 3-ish, 10 to the 38 ergs per second. But this was 10 to the 36 ergs per second. So this is a really low luminosity source. And we still didn't know what the nature of the accretor was based on the MAXI observations. So I took a deeper dive into the NuSTAR observations. And so here I'm showing the first observation, the light curve from the first observation that's at the peak of the outburst, and the light curve of the second observation in the sort of long tail of the outburst many days later. And I've extracted spectra from these two observations that I'm showing here. And so this is kind of small, but I just want to show like the dramatic difference in shape between the spectra. We're really seeing that evolution from something with a lot of thermal emission, right? Lower energy around, below 10 kV. We're seeing that big bulge in the spectrum representing the disk. And that falls off very quickly, whereas in the later observation, as the disk had kind of receded, we see instead just kind of a power law, right? And so there are hot plasma, the corona is dominant. And if you have a keen eye, you can see that there's some emission here, and that's right around the iron line complex, 6 to 7 kV, which provided a useful tool for understanding this source. So one of the reasons that iron is such an important tracer for X-ray binaries is because we can perform what we call reflection studies. Essentially, iron in the disk is fluoresced by the emission from the corona or from neutron star surface, depending on the kind of system we're looking at. And generally that when the iron re-emits, right, you would expect to see just narrow lines, right? If the iron is just standing still, far away from a black hole or neutron star, then you would just expect narrow lines. But what we see instead are these broad, like dramatically broadened iron lines with this long red tail. So energy increases to the right here. So red is that way, right? So we have these broadened iron lines. And what that represents is red and blue shifting in the inner regions of the accretion disk due to general relativistic effects. So we're getting really close to that deep gravitational well due to these objects, and combined with special relativistic effects, which I think is really well represented by this sort of simulation here. So this is, I think, the results of a ray tracing simulation of an accretion disk with a black hole accretor right here, right? So this block is just zoomed in on the disk here, and this is what it would look like to an observer at infinity. And so more red here is the emission is more red shifted, more blue is the emission is more blue shifted. And so you can see as we get closer and closer to the black hole, there's a lot of red shifting due to one, the receding disk. If the disk is going like this, right? We have the disk is receding on this side, and we have this deep gravitational well causing a lot of red shifting. But then on this side, we have blue shifting instead as the disk material comes towards us, right? So essentially by modeling these broadened iron lines, we can study this region right near the disk, right at the sort of innermost stable circular orbits and near there. Yes.
Is this meant to be a flat disk and it's just being warped because of the sort of light path of the back of the disk coming toward it?
Exactly. Yeah. So this warp is supposed to be is the result of just light bending. Yeah, but it should be flat. But I mean, yeah, we do see warping in disks in general, but it doesn't really quite look like that. Yeah.
Are there like observations enough to test GR or that?
In the sense that the ray tracing models do describe the broad iron lines, yes, but I don't think that it's like a meaningful test of GR compared to other experiments. Does that make sense?
Well, I guess.
I mean,
I haven't. What do you mean, like other experiments, like related to this? I guess I'm just wondering if this is like a smoking gun, right?
Of GR?
Like, yeah.
Yeah.
But I guess. But I'm just wondering too with the accuracy, because you don't know the information anymore, right? There's like a lot of unknowns. You have to model it just exactly, like understand the system exactly to be able to have a comparable estimate compared to, like mercury, right?
Right.
I was just wondering if this is like, has anyone gone down into your path with these types of observations? Because it's not my field, so I haven't.
Yeah, no, I think that's not quite feasible because of a lot of the systematic uncertainties.
Okay.
Right. And
And
there's
also
a
too with X-ray telescopes, they're not. Yeah. The resolution is not great.
right. Yeah, it's limited depending on the resolution and things like that, but it does, these models do a like dramatically better job of describing the broadened iron line than if you were to just stick a broadened Gaussian or something like that. I think there was another question.
Yeah, Does like the asymmetric line shape imply an asymmetric disk in this case, or am I just like misreading this?
Right, so because it's more reddened. So that doesn't imply an asymmetric disk. It's just the nature of it's like the GR is out competing the Doppler shifting on the blue side.
Got it.
Yeah. And these are coming from like different regions in the disk and that kind of thing.
Another question, because this is iron lines, right? So is this
Mhm.
like a solar metallicity kind of system is usually what you're looking at?
So a lot of you can model the metallicity, and so digging deep into these models is not necessarily my expertise, but my understanding is that most of the time when you do model the metallicity or the iron abundance, it's much higher than solar, and that's kind of a question of like why. Right, because it's just material coming off of a star, right? So it shouldn't. Yeah, I think that's still kind of an open question. Is that a problem with the models? Is there some kind of degeneracy there, right? Where it's, if we push something else down, then maybe our metallicity is more reasonable, or is it really like we're seeing something happening, right?
I mean,
Yeah.
iron is depending on the source, iron is one of the main line drivers for
Mhm.
winds, right? So you could expect some enhancements of like super solar. Let's say objects were rich in solar, maybe you expect super solar.
Mhm.
Are you able, or is it that because you get this reddening or the resolution isn't great enough that you can't really infer like an iron abundance? Or
So you can infer an iron abundance, and I mean if your data is really good, right? You can. do
yeah,
that.
I wonder, is data good enough?
In this object, I don't think I did, or I didn't worry about it. It's probably not very well constrained. Yeah. Because these are pretty short observations. Yeah. I'm gonna continue. Steve?
I was
Yeah.
just gonna say, in terms of the testing GR, I think these observations usually turn that around, and so they use GR to model from the lines to model what the spin of the black hole is and what the inclination of the disk is. Usually it's assuming GR is correct and using that to infer geometry.
Mhm.
Is that
Yes.
right?
Yeah.
Okay.
Yeah, instead of vice versa, because we
Well, I
don't,
wonder if you had
if you
to
don't
prove the
independently-
observations, they knew everything.
if we knew the spin and if we knew
Yeah.
the inclination,
But
then we
there's-
could use it. So but
Okay.
usually it's the opposite. So.
Yeah,
Right.
yeah.
And a possibly unrelated question, are the amplitudes of the iron lines important here? Because it looks like during the not flare up, the iron is stronger. Like the amplitudes, like,
So here is stronger than this.
yeah, like peaks at 10, whereas during the flare up, it peaks at like 8.
Yeah.
Or is that not real or noisy or?
So that can happen for a couple different reasons, right? The geometry of the system that we're looking at can change over time in terms of what we call the reflection fraction, right? How much of the material, how much is the iron being fluoresced, right? And how much of the disk are we able to like light up with the corona or something compared to other? But I think this is also, it's hard to tell because as I'm about to show, there's also some narrow components on top. So what I found is that in addition to this broadened feature, even when I stuck that in there, I still have these like narrow peaks here. So yeah, some of the reason that this looks so much higher is maybe because of that narrow peak, right? And the narrow peak represents, physically what that means to us is that there's a region of iron being fluoresced somewhere far away from the inner regions of the disk. So it's not experiencing that kind of, yeah.
Well, and can you, I mean, I would suspect like the inner disk, right? The midplane would be hotter too, so you could get some, like those. You get higher energy X-rays that would be less likely to be attenuated, so that also misses things to like makes it difficult, right?
I'm not sure what you're saying.
Well, I guess it's like the accretion disk is not a constant temperature, right?
Uh-huh.
So like when you get towards the midplane of the disk, you should have hotter material.
Yeah, right.
And that should affect also like the X-rays like you're seeing.
Right,
So you get a
exactly. Yeah.
distribution of thermal X-rays.
Yes. Yeah. Okay, I'm going to try to zoom through here. No problem. These are good questions. I think the reflection modeling is like one of the most interesting parts of this work. So yeah, so initially what I tried to do is just model each of these spectra separately. So we have these two different, you have two spectra at two different times in the outburst, right? One is at the peak of the outburst, one is kind of near the end of the outburst. And when I try to do this, don't worry about the actual text or anything. What I'm trying to show is that when I did like an MCMC study of the parameters of those spectral fits, and I find a lot of degeneracy, and it's really hard to constrain stuff, right? So what this is kind of indicating is that like at different times in the outburst, right, essentially different geometries of the system, we're sensitive to slightly different parameters in different ways. And so what I did is I performed a joint fitting that helps us kind of take the strengths of each observation and combine them to get good measurements of the parameters that we're interested in. So as Anna mentioned, and as Steve mentioned, we want to know like the spin of the compact object. That's going to tell us about the nature of the object itself, right? Spin here being sort of a parameterized version of the angular momentum. And then we want to know the inclination of the disk because that helps us get out the spin and et cetera. And then also we want to know how far in, so R in is the innermost radius of the disk. We want to know how far that disk comes to, or how close it comes to the compact object. And so by doing this joint fitting, again, don't worry about the numbers, but it's cool to look at. We definitely push down the degeneracy between a lot of these parameters and are able to constrain them a lot better. There's still some like dramatic degeneracies, but some of those are impossible to avoid, right? Between, for example, the spin and the innermost radius are degenerate because physically, the faster you're spinning, the closer and you can go to the black hole. And so, yeah, we get a good constraint on the spin. It's nearly maximal. So essentially this thing is spinning it almost as fast as possible under GR. We got the inclination, doesn't really matter. And then the inner disk radius, we see evolution over the course of the outburst. So when the thing was really bright and hot, the disk was coming essentially as close into the black hole as possible. And then later on, it looks like that disk doesn't come as close. So we're seeing what we call moderate disk truncation. Okay, and so you'll notice that I've been referring to it as a black hole now, and that's because that spin parameter that we get, the maximal spin parameter, indicates that it's probably not a neutron star because neutron stars can only achieve spin parameters of around like 0.7 before they start to break up, right? So it must be something that doesn't have that physical extent, so it can't break up.
Well, an RG is tiny compared to the truncation radius. For, for magnetized neutron stars.
Exactly. Yeah. So yeah, multiple reasons from our spectral analysis why it's probably a black hole. We see, we got the inclination and we got evidence for mild disk truncation. And then going back to those narrow lines, those could be different, like areas in the disk of different ionization, or they could be like outflows with different, like a blue shifted outflow and a red shifted outflow or something like that. Okay, so by studying this, by using NuSTAR to study this transient X-ray binary throughout its outburst, we were really able to do an analysis of the properties of the compact object itself that would not be possible with other observatories or with just like one observation during the outburst or something.
Does RG depend on the pressure, like the truncation radius, the magnetic pressure?
So I think there's still a decent amount of debate about like why the disk is truncated around a black hole in particular, and like how much it's actually truncated, right? I think some people would maybe argue that it's not actually truncated, but there's changes to something like, I don't know, disk ionization or something, or changes in the corona that are causing the differences in the reflection spectrum. But,
okay, I guess I'm just wondering if like that difference in RG, or sorry, the RN from 3 to 8, if that could do it, if anything with the accretion rate changing during that, where maybe you have a lower accretion rate at the hard state.
yeah, absolutely, it's a lower accretion rate.
But that would
might
make sense for magnetized. I don't know.
Right. Yeah, I don't have a great answer for you, but yeah, we do see evidence for shift truncation at least. And so the next one I'm going to try to get through relatively quickly, if that's okay, is a neutron star. And so this is one that I've been working on just recently. So some of this might change, but I think I'm at a point where it's not going to change, hopefully. Oops. And so this was another transient near the sun that went off last summer, like right before. They always go off at the most like inconvenient times. Okay, the other one was right before I was going off for break. And my collaborator's like, Sean, you're a grad student, do you want to do it? Sure. And then this one was like right before I went to defend my thesis. So I kind of just like sat on this data for a long time. But now it's become a really interesting source. So as part of a NuSTAR program that I have to perform follow-ups on sources near the sun, like the previous one, I sort of used that previous case to make the case that this should be like an official program. And so I applied and got that time. This went into outbursts near the sun, was seen by Maxi. And so we got our NuSTAR follow-up because other observatories couldn't do it. Right. And so here I'm showing the Maxi light curve again. You can see it going into outbursts. There's a lot of like kind of shorter timescale variability that I'll get into. We got this first observation right around here. So near the beginning of the outburst this time. And then a second observation was proposed for much later, about 50 days later, when it's kind of simmered down again. So again, we're looking at this transient outburst at different points in its evolution. And using NuSTAR, we found that this previously unknown object shows really strong pulsations. This is evidence that it's an accreting neutron star right away. And that throughout the outburst, the period of pulsations, it's covered up, went from, so at this stage, the period at which the neutron star was spinning was 1130 seconds. And it got faster and faster throughout the outburst until its period was 1080 seconds later on. So this is a relatively high spin up for these sources. Optical observations by people who are not me identified the companion as an OB star. So this is one of those sources that I mentioned earlier, where we have a high mass companion. In this case, probably something like 20 solar masses. The neutron star is in a highly elliptical orbit around the companion. And when it comes in to periastron, it picks up a bunch of material and has this transient disk. And that's what we're seeing here is that that disk is forming and then draining away as it gets farther away from the companion. Yeah. So as I mentioned before, pulsations indicate a magnetized neutron star. So we expect to see some kind of truncation and things like that, where it's funneling material onto the neutron star surface. And so the approach that we wanted to take is to use 3 different levers to measure the magnetic field of that neutron star. Okay, and so the 3 ways we did that are through spectral analysis of the NuSTAR observations, Fourier analysis of the light curves from NuSTAR, and an analysis of the long-term spin evolution of the system. So we saw that that the thing spun up really fast, right? Okay, so one of the best ways to measure the magnetic field of a neutron star is to look for cyclotron lines. So essentially, cyclotron line absorption features are formed due to coupling of charged particles in the strong magnetic field of the neutron star very close to the surface. And in these cases, those charged particles, electrons and protons, are their energy levels are quantized into states that are the energy states that are directly proportional to the magnetic field that they're in, right? And so we get out this relatively simple equation where the energy of this absorption dip that we see is proportional to the magnetic field via this constant of proportionality. And so we saw something here in the spectrum. So here I'm modeling the NuSTAR spectrum. It's a much simpler spectrum than before. We don't see things like reflection. What we're just seeing probably is that accretion column mainly. And we're seeing like comptonization in that accretion column. But we see this little dip in the residuals at around 45 keV. And it's not super, what's the word? Significant, right? It's probably less than 3 sigma, but it's there. We wanted to say something about it. So when we plug that into this equation, we get 5 times 10 to the 12th Gauss. So that's pretty standard for these kinds of sources. The problem came in when we started doing our other analyses and found that they don't agree at all with that measurement of the magnetic field. So the other lever that we used to study the magnetic field was to look at to do a Fourier analysis of the light curve to see how is the brightness varying in the NuSTAR band throughout that observation. And what we found is, in addition to pulsations, so these peaks are pulsations that we saw, we have this other broader peak, which we refer to as quasi-periodic oscillations. And in these systems, these are attributed to essentially activity right near the inner radius of the disk. So either some kind of like instability in the disk that modulates the accretion rate onto the star. So yeah, that creates some variability, or it can be like a bulge that's kind of like modulating obscuration. Either way, essentially what these models allow us to do is to equate the frequency of these oscillations to the Keplerian frequency of the inner regions of the disk. And if we assume that the disk is truncated due to the magnetic field, right, then we can relate the strength of the magnetic field to this radius here, right? So you plug it into this big equation here that includes the frequency, it includes the accretion rate, et cetera. Then you get a magnetic field of 2 × 10⁻13 joules. Okay, that's a factor of a few bigger than what we saw with the cyclotron line. So the next thing we did and was to model the torque that was applied to the neutron star by accretion throughout the entire outburst. And so we were able to do that thanks to Fermi. Fermi is a gamma ray telescope that is able to monitor pulsars in the X-ray as well. So Fermi was able to trace the frequency of the neutron star throughout the entire outburst, right? So we had in orange here, I'm showing the frequency that we measured with NuSTAR during the outburst. Here's the max count rate again. So this is kind of smoothed out what the outburst looks like. And you can see that it traces this outburst really well. So at a high luminosity, our derivative of our frequency is high, right, et cetera. And so what that's indicating is that this spin up that we see is due to the accreting material actually exerting a torque on the neutron star. And as I said before, luminosity or brightness is directly proportional to the accretion rate. So at a higher accretion rate, faster spin up. Okay, and so there are a few different models for understanding this spin up rate. We chose basically the most common one, which assumes again disk truncation due to the magnetic field, and it assumes that the torque is exerted at that inner disk radius. And so what we get is the magnetic field is proportionate to the this combination of the luminosity times, or the luminosity to the -3 and the spin up rate. So how fast the thing is being torqued to the 7/2. And so when we fit that, we get even higher. So something like 10⁻14 joules. Okay, so numbers are not adding up here. We get wildly different values, and I don't want to get into the weeds too much, but essentially, I think just throw out the cyclotron feature. It's not a great significance, but it's also way narrower than we expect these features to be. So essentially the physical picture doesn't quite add up. If we expect these things to be the cyclotron absorption to be happening right near the neutron star, then we expect the electrons that are doing the scattering to have a broad thermal distribution, right? So those absorption features should be broad, right? But that's not what we see here.
What about like winds from the neutron star interacting with the magnetic field also removing momentum? What did you take that into account rather than just the truncation model?
Yeah, so you're saying like yes, spin down due to
Over. Yeah, no, I did something similar for massive star formation. So taking those models where they started out with the neutron star spin down, then they've been applied to T-Tauri stars, and I applied it to massive stars, right? And so you could also, if you have these driven winds, if there's accretion powered winds,
yeah,
we can talk about at lunch, but there might be other spin down or spin like things that to take into account.
absolutely. Yeah, so in its quiescent state, that would be a good opportunity to do this kind of measurement, right? When there's not accreting material applying torque, then you would assume that winds from the neutron star are spinning it down, right? But the accretion is spinning it up, right?
Yes. Oh, yeah. Then that would lead to, yeah.
Yeah.
We bet time.
Yeah, I'm gonna wrap up. So yeah. I think, what was I saying? So throw away the cyclotron line. The other two don't quite add up, but essentially, if we invoke kind of systematic differences that have been seen in spin up rates in other systems, then we can get them to agree that the magnetic field is probably high, above 10 to the 13 Gauss, which is really high for these sources and puts it in the range of like a magnetar-like neutron star. And so I'm just gonna, I had one more, but I wasn't actually planning to hit it. I just have it as extra. So that's about it. So hopefully I've showed that transient accretion onto the black holes and neutron stars is interesting. It provides like a huge variety of phenomena that we can study in the timing regime, in spectral regime. And using X-ray observatories like NuSTAR, we can investigate a bunch of different characteristics of these sources and of accretion in general. Thanks.
Questions online or in the room, George?
I have two questions. So they both relate to dark matter,
Okay,
not.
probably can't answer them, but go ahead.
But it does relate to X-ray photonics. So first question, just curiosity. New stars detectors don't have very good energy resolution from my perspective.
Okay,
So could you have something like New Star that can, that can gather an image, high energy X-rays up to 79 keV or whatever, but have a calorimeter with a high energy resolution like you're going to have on Athena, if Athena ever happens, or Prism, which probably will happen, but which will be a miserably small telescope. That's my first question.
yeah, so I think one question is, why do you need high spectral resolution above this like 10
Because we
keV?
want to resolve the line width
Yeah,
for potential dark matter candidates to decay into X-rays.
okay,
So because you could get a smoking gun for actual dark matter if that line width is a virial width
mhm,
instead of a width that reflects, thermalized ions in some way, which would be
Right.
a much narrower width, for example, in a cluster of galaxies. So that's the reason.
Yeah.
I'm just wondering technically whether anyone has thought about that or pitched that.
yeah. I mean, calorimeters are the best way to get really high spectral resolution, and they just don't. Nothing wrong with the calorimeters themselves, but they just, for whatever reason, have not panned out, right? Like Hitomi was supposed to have a calorimeter and it exploded.
We
Right?
all
So-
know about it.
Yeah, so- but I don't see why it wouldn't be possible technically. Although I'm not an expert on calorimeters as detectors, I don't know what kind of like spatial resolution you can get with those.
I would imagine, well, I don't know, but maybe it'd be fun to talk about this at some point, Steve.
Yeah, there's been, so there have been people that have been developing very, very high resolution detectors, and you don't know the line energy, right? So,
No, we do.
okay.
Where is
Tell me what it is.
Well, I mean, there'd be a candidate line. You don't know whether it's an atomic line or something from atomic physics in some way, like charge transfer or whatever, or whether it's a dark matter origin line. So in fact, if you look at clusters of galaxies, there are a hell of a lot of lines. So
Is it below 10 kV or more? Or could you go?
well, this is the thing about New Star is it can look up, with some
Yeah.
sensitivity above 10 keV, whereas CCDs don't do that. So
So there has been work on very, very high spectral resolution superconducting detectors that go up into the financial range. There's just never been a really good science case for flying them. So if you have a science case for flying them,
anyway, so thank you. Let me get to my second question, which is more related to your topic.
Okay.
But it also has to do with dark matter. So one signature of dark matter might be WIMP, anti-WIMP annihilation or something like that. Dark matter annihilation, black center and gamma rays that come from that.
Mhm.
Here's the problem. If you make an estimate of what the spectrum, the SED looks like for that, for those gamma rays, it's almost coincident with what you expect from millisecond pulsars.
Hmm.
So how many millisecond pulsars are there in the galactic center? And so there are these surveys that basically use low mass X-ray binaries as a tracer. I'm just wondering if you thought about any kind of surveys like that, looking at low mass X-ray binaries.
So you're asking like surveying low mass X-ray binaries to determine the number of millisecond pulsars.
Or
in
at
the
least
galactic
get an
center.
idea of how many mils that maybe the galactic center has more than
Right.
some number of.
I don't know the numbers off the top of my head, sorry, yeah. I don't think I have a good answer for that. Yeah.
Thank you. Is the telescope you're looking on now better than the star or just different?
It's very different, yeah, so COSY is what I'm here to work on. COSY is a soft gamma ray telescope, so totally different band pass, right, from 200 keV to 5 MeV. And it's more of it's like an all sky imager sort of, and it'll do very, very different science. But I think that there's a lot of potential to study X-ray binaries, particularly those that we see their spectra like extending towards higher energies. But yeah, it's hard. I wouldn't really compare them because they're doing very different measurements.
There's something in the chat.
Then didn't drop down again.
Oh, really?
It's not.
If the dip isn't from cyclotrons, do you have?
That introduces a lot of kind of finesse into extracting the spectrum. One of the issues in that observation in particular is that the source landed close to the edge of the detector. It landed close to like the gap between chips. So it's hard to say. I think it could be, yeah, something in the process of extracting the spectrum. It could also be the the variability of the source at about 1,000 seconds is close to, it's like a similar time scale to the variability of like how like the bins that I'm extracting the spectrum, right? So there could be some kind of like dip or something there that's just moving around and causes this like absorption looking thing.
I guess, so you look at, like cyclotron, what about synchrotron? You expect relativistic electrons from?
I don't know. I'm not
what that, I don't know. Yeah, what band it, but like, is that another consistency check for?
I don't think that folks usually see synchrotron in this band from these sources, but
Would it be in radio? I don't.
well, it depends on where you
Oh, I didn't know
saying
the
it's
Richards
coming
would know, right?
from. But I mean, there's synchrotron, so there's sorry, so synchrotron emission in like black hole systems will pop up in radio and show a jet,
Yeah.
right? But yeah, in terms of the X-ray spectrum, I don't think that.
Well, I'm saying like if there was an instrument that could follow up on the synchrotron.
Right,
that.
we didn't see any radio emission from this source, if that's
Okay.
your question. Yeah, so
But I would expect that you get relativistic electrons from the accretion shocks anyways, right? So if you're seeing cyclotrons, you have.
so the cyclotron line is happening because we have this like shocked accretion column, right, which is very small in kind of extent, right? And the thermal electrons from inside there are being like scattered as they come out.
Yeah, so you'd be dominated, but shouldn't a tiny fraction go into accelerating electrons and
So
protons and cosmic rays? That then.
maybe.
Okay.
I don't know. All I can say is that we don't see radio emission, and yeah.
What about, you follow Fermi, you see, no. I'm thinking about the gamma rays, but.
Yeah, I mean, we got like gamma ray fluxes out of it, or soft gamma rays, I guess, or high or really hard X-rays, but yeah.
Any last question? right, thanks, Sean. For SDSU grad students or UCSD grad students that are online, Preeti is going to take over hosting for the post-doc Q&A. And we'll come back and get you in about 15-20 minutes
Okay.
for lunch.
Sounds good.
If anyone is interested in meeting with Sean this afternoon or joining us for dinner, please let me know ASAP. Thank you.
Did I leave this up, I guess?
It's totally up to you.
Okay.
Yeah. Well, yeah.
I didn't think so.
All I want to know is how.
So, yeah, the reason I just, but also because, so I split it up into like these different factors, right? It's based on which star factors were. That's because it's near the sun. But, what I didn't see that is for in the other plans. And so for now, I'm just saying. It might also depend if it's something like it's background or something like that. It's not an instruction, so I'm ignoring it. Where it's the narrowed, you see.
Interesting.
Either it's something systematic for all the.
You might have to, there's this thing that you can do. Okay. Which is you go to like the. Shell or RC on.
Oh, I got it. Cool. All right. I'll catch you later. I won't be able to join you for lunch. I have a meeting, but I might be able to catch you
You
with
go to
dinner.
like some files, not bash RC. Then you can do this thing like export and then like a name and put a tab on it, and it might show me like run stuff. It will like have that filter. I don't know if that's like the issue, but I feel like maybe with I definitely, I've had to do this with a lot of like ideas, like I have to.
Well, not confused, I guess, I just like specifics on. You said, so like the thing happened, right? And then you did the follow-up. That seems like a very fast turnaround for like a proposal.
Right, yeah.
So how does that work? Like, just, I guess, like logistics of the proposal, like to be able to say, I need to see this and then hear back, because it's such a short window, like you
Right.
need to.
Yeah, so two things. One, yeah, Newstar was my advisor. in
Oh,
topics.
Okay.
But even so, like,
Yeah.
so the first observation that I showed, the black hole where we followed up and it was kind of near the end of the peak. I did that, I proposed through director's discretionary. So the Newstar website has a link where you can go and at any time, you can say, I want to look at this thing. And I want to look at it with this kind of turnaround. And here's why I want to look at it, et cetera, right? And you're not competing with other people when you propose that way, right?
Oh,
And so it's really up to Fiona, essentially to say, based on like, first of all, based on like the gaps that Newstar has in its time and based on the scientific argument that you put in, whether she thinks that you should go with it. So that's where I got the first one. The second one I actually proposed to the community ahead of time, right? So through Newstar's general observer cycle, I proposed to do this exact kind of follow-up. And so that way, when the thing went off, I just reported it to the Newstar team and said, hey, this fulfills the criteria that the community agreed should be like observed, essentially that follow should have happened. So yeah, but Newstar is pretty flexible. It's able to follow up relatively rapidly. And yeah, my understanding is that they're like, it's not like it's always observing something.
Okay.
Right. And so there are gaps that can be filled with that kind of like rapid follow-up.
Thank you.
Uh-huh.
I was gonna ask, I was wondering if you could go into a little bit more detail about like disk truncation. 'Cause I haven't really heard that term before and I.
Yeah. So let me see if I can. New slides. So, yeah, disk truncation can happen for a couple of different reasons, right? So it's happening in black holes for different reasons than it's happening in neutron stars. In neutron stars, we expect disk truncation when the magnetic field is very strong, right? And so essentially the disk is made up of it's of like charged particles, right? And the charged particles become coupled to the magnetic field because it's so strong. Yeah.
And when you say like disk and neutron star, is that like simply when they have a binary and they're picking up material from the other star? Okay.
Exactly. Yeah. So the accretion disk only forms in these binary systems where material is falling from the computer. Yeah, exactly. And yeah, so essentially the magnetic field like grabs the stuff out of the disk and pulls it towards the neutron star surface, right? Basically, right? And so it's not halting accretion, but it's changing the shape. And so we don't see the same like disk spectrum, right? We don't see that that multicolored disk black body all the way up to the surface. We see it kind of like stop at a certain radius and then change into like the accretion column or something, right? In some neutron stars, there's not truncation. Those that have been accreting for a long time, their magnetic fields have been worn down essentially, and they no longer truncate. And in those cases, what we see, or what's theorized, I guess, is that the disk comes up much closer, and then it's truncated by what's called a boundary layer. Right. So near the neutron star, essentially the material has to the material in the disk has to at some point get to the same rotational velocity as the neutron star itself, right? For it to like actually land on the surface. And so there's sort of a layer around the neutron star that I think is just like a few kilometers to maybe like 10-ish kilometers, right? But comparable to the radius of the neutron star itself, where we no longer have a disk, but we have this kind of puppy boundary layer where stuff is sort of like coming to it's slowing down to get to the same rate as that, or maybe it's speeding up actually. I don't know. Anyway, depending on the neutron star, I guess. But yeah, and then in black holes, the picture is a little less clear. I think part of the one thing is determining how the extent to which disk truncation happens in black holes. But if it does happen, the idea is that for whatever reason, it's essentially turning from this what we call a thin disk, right? It's called a thin, like cold disk model, but it's cold relative to like the plasma that's like in the corona, right? The corona temperatures are like tens of Kelvin, right? The disk temperatures are like a few Kelvin, 1, 2 Kelvin, right? So we have this thin cold disk, but then in black holes, it may be the case that at some point, maybe due to like interaction with the corona, that transforms into what we call an advection dominated flow. So it's no longer Keplerian, and it's kind of this like hot plasma that just flows into the black hole. And so that's what we mean by disk truncation. So in both of these cases, it's not as if the material just stops, it's just hanging out there. It's still accreting onto the thing, or sometimes it's being blown outwards by the luminosity. But yeah, it's more just that the disk transforms into some other kind of shape that we would no longer call this. Does that make sense?
Yeah, I think so. Also, I was wondering, what are the like energy range, or like what are the I don't remember the name for it, like Gauss, what are the ranges for the magnetic field that you need to
truncate the disk?
Yeah, like you said that it happens when you have strong magnetic fields, right? So what is the range?
So I
say that, sorry.
it's no, I didn't say. Yeah, so it's essentially like 10 to the 12 Gauss and up.
Okay.
We see in these what we call high mass X-ray binaries, right? These are where we see pulsations, right? When we see pulsations, that means we have this like funneling taking place. And when we don't see pulsations, it can still be a neutron star, but it's just that it just turns into this boundary layer. So we're just seeing this like sphere of stuff. And so there's not a mechanism that's producing pulsations, right? And so when we see these pulsating, accreting neutron stars, we measure their magnetic fields. They tend to be like about 10 to the 12. Yeah.
How long did your joint fitting routine take?
Not too bad, yeah, I don't remember, I mean, maybe a couple hours. It wasn't, yeah, it wasn't. crazy. Although, yeah, actually performing the MCMC, like to get the parameter. Like the distributions of the parameters, that took a lot longer, maybe. Maybe like a day or something like that.
Yeah.
Yeah, so the way I do is, when I want to do that kind of like MCMC is I just do least squares fitting first. To get like the parameter, and then I just to estimate the parameter errors, that's where I do the MCMC. And all of that's built into expect if you do X-ray astronomy, it's all built in, so cool. Makes sense.
You mentioned like this brain neutron star. What would you mean is this? Like how, I don't know, I guess I would think of it as like an
Yeah, so the spin parameter is unitless. But it's yeah, but it's something like JC squared over M or something like that, right? So it's essentially pulls out like the mass dependence.
And J is the angular.
Yes, J is the angular momentum. That's yeah.
Also, on one of your plots, you have an alphabet.
Yeah, that's
What is that?
oh,
You do that one.
yeah, so we just so essentially the reason for that is just to label the different these points, right?
Oh,
Because in the paper, we're also for each of these points, we're plotting for each of these intervals labeled A through T, we're also plotting like the pulse profile and stuff. So it makes it easier. Yeah, but in this case, you don't need that.
you went to Brown. What
Yes.
was your favorite restaurant?
Gotta be East Side Pockets. Fucking love East Side Pockets. Did you go wrong?
I'm from Rhode Island.
Okay.
So, yeah, I grew up like in a.
Okay. I love Robin too. Fuck with that.
I have a quick question.
Uh-huh.
So can truncation happen with whiteboards that have some fields?
I don't study white dwarfs,
Uh-huh.
so
Okay.
I'm not sure, but
In theory?
I'm not sure the strength of the magnetic fields that you would, I mean, there's no reason it can't happen, right? Except that I don't know what the magnetic fields you would expect there or the radii. Right. Because it might be that whatever the truncation radius would be smaller than the actual radius of the
Oh,
white dwarf. So, yeah, probably one of the representative stuff.
I have a question
Sure.
more about kind of like grad school stuff.
Uh-huh.
Are there things that you did like for this work that went into your thesis and thesis defense that you're like, oh, I'm so glad I did that? As a, like, yeah.
Let's see. I mean, I think proposing for observations for sure is like, I mean, it's super, super important. And hopefully during grad school, you get an opportunity to do that. I think, I worked relatively independently in grad school. Probably that was just my advisor's style. It wasn't like I was just like ready to go. I was not, but yeah, so I think I liked doing like this broad kind of focus in a lot of ways. And I'm studying like different kinds of objects, right? Neutron stars, black holes, low mass sector binaries, high mass sector binaries, etc. In some ways, I think that was a good thing because I have a relatively broad understanding of like the tools that are necessary and the different kinds of analyses, timing and spectral analyses, things like that. At the same time, sometimes I kind of wish that I had had a more focused kind of like, here's the key question I'm looking to address and chase after that, which I didn't really have. But yeah, it's hard to say. I mean, it's really dependent on what your field of study is and that kind of thing. But I do think proposing for stuff is like one of the most important things to like learn how to do. So if it's possible to get that kind of experience out of it. Cool. Thanks.
We're good here. And I'm probably expecting you for lunch too, so we don't
Yeah.
want to take up too much of your
You're
time.
supposed to come get me if I'm supposed to go get that. So, thanks for
Thank
coming.
you.
Thank you.